Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is part of a series of lectures on computer architecture. So, we are looking at control unit design in the area of computer architecture. So, when we talk of control unit design, we have looked at some basics of how the design needs to be done, how the different control signals have to be generated. And in the previous topic, previous lecture, we looked at a topic called pipelining. So, we talked about introducing pipelining in order to improve performance. And then with respect to the MIPS architecture, we saw how the pipelining can be done. We saw that the MIPS pipeline can basically be divided into 5 stages: the IF, ID, EXE, MEM and the write back stage. These are terms that we will keep repeating often. So, by the time we come to the end of computer architecture, you will be very familiar with these terms. The 5 stage MIPS pipeline is used as a standard for understanding many concepts. Okay. In today's lecture, what we will be looking at is some of the issues that occur in a pipeline design, and we will also look at some more details on the design as such. So, a quick recap of what we have been looking at in the previous class. So, if you look at this idea of pipelining, we see that we are able to get better performance or finish things faster in a pipelined architecture just by starting a job, starting the next job even before the first job finishes. So, that is the idea. So, if I have 5 different subtasks, the IF, ID, ALU operation, data access and register access. Now, I do not wait for this entire thing to be completed before I start the next instruction. I can start it as soon as the fetch is over, which is what we are doing here in the pipelined access. If we do this, we are able to do, you can see that at any given point of time there are many things happening in parallel. Therefore, the overall time taken is reduced. So, this is what we saw with respect to pipelining. Now, the question that we look at is pipelining just so simple? Okay, the answer to that is, it is basically yes, but of course, there are some issues that need to be handled. So, what are these issues that need to be handled? One of the primary problems that we have with pipelines are what are called as hazards. So, we need to understand what we mean by these hazards. So, if you look at a hazard, in very simple terms define it as any situation that prevents starting the next instruction in the next cycle. Now, remember, idea of pipelining itself is based on the fact that in every clock cycle I should be able to start a new instruction. So, which obviously also means that every clock cycle I will be finishing one instruction. Okay. So, that is the fast execution that we are expecting. So, if there is any situation that is preventing you to starting the next instruction next cycle, then we say that we have a hazard. Okay. There is a pipeline hazard. Now, this pipeline hazard can occur due to various reasons. It may be what we call as a structural hazard. So, what we mean by structural hazard? This means that some structure or some resource which is required is busy, is being used by some other instruction. When a resource is busy, is being used by some other instruction, then obviously another instruction cannot use the same resource. So, then we say that the pipeline cannot proceed further, and therefore, we have a structural hazard. Okay, this is one hazard to look for. Second is what is called as a data hazard. Now, this happens when we need to wait for the previous instruction to complete its data read or write before you can start the next instruction. Now, remember, there will always be dependency between instructions, okay, and the dependency could be a data dependency or a control dependency. So, what we mean by data dependency is that the output of one instruction will have to go as input to the next instruction. Now, obviously, until the output has completed, until the previous instruction has completed its output, has written the data, the next instruction may not be able to read the data from the register. So, in which case you may have to wait until the previous instruction completes before the next instruction can start. So, in this case we say we have a data hazard. Okay. The third is a control hazard. Now, this happens whenever we have control instructions in place, that is, the deciding on the control action depends on the previous instruction. So, let us say we have a branch on equal instruction. So, now if I have a branch on equal instruction which has come into the pipeline, just let us say it was in the IF stage, now it has gone into the ID stage. Now, when the question is, in the next clock cycle, which is the instruction I need to fetch. Since we have a branch on equal instruction, based on the outcome of the branch instruction, that is whether the condition was met or not, you would either be picking up the instruction which is coming in sequence, or you will be picking up an instruction from what we call as the target address, from wherever you are supposed to jump to. So now, which instruction is coming into the pipeline? I can't decide that until the branch outcome is known. So here again there will be a delay for me in deciding which instruction can be brought into the pipeline. So this we call as a control hazard, that is, it is some problem that we get because we do not know in which direction the control has to go. So we call this as a control hazard. So therefore there are these three types of hazards that we need to watch out for: structural hazard, data hazard and control hazard. So three hazards that we need to watch out for and that we need to prevent. So as we said, structural hazard happen because of conflict for use of a resource. An example for a structural hazard in our MIPS pipeline would be, actually if we had used a single memory for both our data access and instruction access, that is, if our instruction memory and data memory were a single memory unit that we had, then we would actually have had a structural hazard. Okay. But what we have actually done is, in the pipeline data path, we have used separate instruction memory and a separate data memory. Now the reason that we used separate instruction and separate data memory itself is in order to avoid the structural hazard. If we had both of them accessing the same memory, you will find that there are two stages: the IF stage, the instruction fetch stage, where the memory has to be accessed, and the mem stage, again where the memory has to be accessed. Now both these accesses of two different instructions cannot take place in the same clock cycle if we had a single memory. So one of the ways in which we handle structural hazards is by duplicating the resource or by splitting the resource or something. So in this case, we have split the resource and said that we have a separate instruction memory and a separate data memory, and therefore we have gotten rid of this structural hazard that we see here. If you did not get rid of the structural hazard, then what would happen is that the instruction fetch would have to wait until that particular access got completed. So we say that the instruction fetch will have to stall for that cycle. Okay, so this term that we use called pipeline stalls. A stall basically means that a pipeline just cannot grow further, it will have to wait at that particular stage. The other instructions ahead can move further, but this instruction will have to wait and not allow other instructions to come in. And this stall, we also call it as causing a pipeline bubble. Okay, this is a term that we use in order to understand what is happening. So we will just take a look at this. Next that we looked at is a data hazard. Okay, so now we said data hazards come because of dependencies that we have. Okay, so let's look at this instruction here. So let's say I have two instructions, an add instruction and a sub instruction. The add instruction is going to add two registers T0, T1 and write it into register S0. This is the destination register. The sub instruction is going to subtract T3 from S0 and write it in T2. Now see, there is a dependence between this add and subtract. The value written by add has to be read by the subtract instruction. So let's look at how this causes a hazard in our pipeline. Now look at our pipeline, we have the IF, ID, EX, mem and write back stages. So the add instruction, let's say, comes in a particular clock cycle here and will move to the next stage in the next clock cycle and so on and finish in the fifth clock cycle, let's say. Now let's say the sub is the next instruction that has to come in for execution. Now where should it have been fetched? It should have been fetched over here. Okay. If it was fetched here, it would have decoded in this clock cycle, and the decode stage is when the register has to be read. So the S0 register, okay, will be read in this second clock cycle, but the add instruction is going to write S0 only in the fifth clock cycle over here. Between this 800 to 1000 in this duration is when the write is going to take place. Okay, but you want to read it between 400 to 600. Obviously, if you read S0 in this clock cycle, you will not get the updated value which is to be got from the add instruction. Instead, you will get some old value of S0. If you access that and continued your execution, naturally the answer will be wrong. So what do we have to do? We have to wait until this instruction, okay, the first instruction will write the value into the register, and only then I can read it from the register. Okay. Now in fact, this writing and reading of registers, if we assume that the writing and reading takes only 100 picoseconds each, we can actually divide the entire 200 picosecond time available into 200 picosecond halves and say that the write will take place in the first half and the read will take place in the second half. Okay. So if you do write here and read here in the second half, at least you can make sure that if you wait for 2 clock cycles and read the value in this clock cycle, the value written by the add will now be read by the subtract. Okay. So, what do I need to do therefore? I do not fetch in the next clock cycle, I do not fetch in the next clock cycle either. So, I introduce what is called as a bubble here, and this bubble is the one that will keep going from one stage to another. Okay. Another bubble introduced over here. So, there are 2 bubbles which will be there. Okay. And then when the first instruction has come into the mem stage, at that time I go and fetch the next instruction, which is the sub instruction. So, that now by the time this comes to write back and writes the register, this instruction will move to the ID stage and read the register in the second half, and so this will now get the correct value, which is the output of the add instruction. So, this is a bubble that will have to be introduced in order to take care of this data hazard. If we did not introduce this bubble, that is, if we did not stall for 2 clock cycles, then we will see that we will have a wrong output at the result of the sub. The sub will not get the updated value of S0, it would have got some old value of S0. Therefore, we have to stall for 2 clock cycles in order to take care of this data hazard. So, this is something very important. So, whenever we have an instruction sequences in programs, we have to look for these dependencies and see if these dependencies will cause a hazard or not. Now, remember that every program will have dependencies. If there are no dependencies, your program may really not do anything useful at all. So, there will be dependencies, but you have to see whether the dependence will cause a hazard or not. Okay. So, if 2 immediate instructions are dependent on one another, a cause of a hazard is possible. So, then we need to do something in order to make sure that the hazard does not occur. Okay. So, this is something that we have to worry about. Okay. So, one of the ways in which you can handle this hazard, okay, is of course, as we saw, by stalling. Now, can we do better than stalling? Can I reduce this wasted clock cycles? Okay. So, if you look at that a little more carefully, we can see that there is something called forwarding, a technique called forwarding, which can be used in order to reduce this stall cycles that we have. Okay. So, let us see how that can be reduced. See, if you look at what is happening here, when the first add instruction gets executed, the S0 value is updated in the register only in this write back clock cycle, but the output is actually available. The value, okay, the T0 plus T1 value is available as soon as it is calculated, which is in the EX stage. That is, at the output of the EX stage at time 600, the value S0 is actually available, but I wait until it is written to the register and then only I am reading it from the register. So, instead of reading it from the register, if I can forward it from the output of the EXE stage to the next instruction which needs it, if I am able to do something like that, then you will see that you can avoid this bubble that comes up. Okay. This is what we will see in this example now. Okay. So, we use this technique called forwarding. That is, what we are saying here is you use the result when it is computed. That is, as soon as it is computed, you can use the result. You do not have to wait for it to be stored in a register. Okay. So, without waiting for it to be stored in a register, use the result as soon as it is computed. Okay. Of course, for this we will require some extra connections in the data path. Okay. Originally, we had assumed that all the reads will take only from the register file. Okay. But now, if you want to forward from the output of the EXE unit back to the input of the EXE unit, you will have an additional data path that needs to be introduced. If we do that, then you can see that with forwarding, we can reduce the number of stall cycles that we have. Okay. So, we will take a short break now and come back and continue. Welcome back after the break. So, we were just looking at how pipelining has to be handled, and we were looking at some of the hazards that occur in a pipeline. So, we talked about 3 types of hazards: structural hazards, data hazards and control hazards. So, we are now looking at data hazard, and we are also looking at a technique which can be used in order to reduce the number of stall cycles that come when you have a data hazard. The technique we are looking at is forwarding. So, we just said that the idea of forwarding is that we use the result as soon as it is computed and do not wait for it to be stored in the register. And of course, for this we introduce a new extra connection in the data path. So, what is it that we need to do therefore? So, you can see what will happen here. So, I have my add instruction coming in the first clock cycle. In the next clock cycle, I allow my sub instruction to be fetched. Okay. But now, in the decode stage, if I read the value of S0, I would have got a wrong value. Okay. but when is this S0 value required? When this instruction goes into the execution stage. When is this going to go into the execution stage? Only between this time at time 600. At time 600, the value is available at the output of EX, right, because add has completed execution. So, at 600 time, the value S0 is available here. So, all I need to do therefore is from the output of EX, if I am able to feed it to the input of EX for the next stage, I can forward the data from here to here, and therefore, I will get this instruction now can execute with the new value of S0 that was calculated by the previous instruction, okay, and then this can continue and do its write. Meanwhile, the first instruction will continue and complete its write in the time period between 800 to 1000. So, this will anyway happen, but all we have done by doing this forwarding is avoided that stalling of 2 clock cycles, which is what we said we would have to do in order to handle this data hazard. So, we can see that this forwarding, or which is also called as known as bypassing. So, bypassing or forwarding is a technique that is commonly used in pipelines in order to avoid the data hazards. We saw an example of a forwarding technique which will allow us to handle a data hazard. Now, there may be some cases where even with forwarding you will still have to have a stall. Okay, let us take an example of that case. Let me take an example of a load followed by an instruction which is using that value of the load, which is loaded by the load instruction. Okay. Now, you will see that you can't always avoid stalls by forwarding. Okay. Now, when is that going to happen? That is when I really need the value. If that value has not been computed, then obviously I can't forward it, right. So, this is what we are talking about, that is you can't forward backward in time. So, forward can happen only if the value is already available and later I can use it, you can't go back in time. So, that is what we are trying to say here. Okay. So, let us look at this example. So, we have a load instruction, load S0 from some memory address given by 20 plus T1. So, now fetch, decode, execute, mem. Now, when is this S0 going to be available now? Remember, not at the output of the EX stage, only at the output of the mem stage, because this value has to be got from memory. Okay. So, the value is available over here. Okay. So, now in the second clock cycle, if I had brought in my sub instruction, so you have a load followed by the sub instruction here, sub $T2, $S0, T3. So, S0 is used by the sub. Okay. So, if my sub had come in the second clock cycle, it was fetched here, decoded here and executed here. Now, remember, when this is getting executed, that value is not yet available. Okay. So, I could not have brought in this IF over here. So, therefore, I will have to stall for 1 clock cycle. But if I stall for 1 clock cycle, then in the next clock cycle, if I bring the sub instruction into the pipeline, fetch it here and decode it here, when it is ready to be executed, I can see that the value is available from the load instruction. Okay. But where is it available? It is available at the output of the mem block. Okay. Or at the output of the mem stage, the value is available. So, from the output of the mem stage, if I can forward it to the input of the exe stage, then with just this one bubble or one stall cycle, I can have the execution of my sub instruction. Remember, if I did not do this either, without this forwarding, I would have to wait for 2 clock cycles before the instruction can be fetched, because write back will happen only over here, only then I can read it and so on. Okay. So, by doing this one more forwarding, okay, forwarding from the output of the mem stage to the exe stage, to the input of the exe stage, you can see that we reduce one stall cycle, you still have one stall cycle. Okay, there is one stall cycle which we still have, but we have reduced one stall cycle. Okay, and therefore, performance improves slightly. Okay. So, you can see that you can't always avoid stalls by forwarding, you may have to have a stall cycle sometimes. Okay. So, this is, so by combination of using forwarding and stalling, you will be able to handle the data hazards. Another technique that is used to handle these data hazards and to avoid stalls, okay, is basically to reorder the code in order to provide a distance between the instruction which produces a result and the instruction which consumes the result. Now, the problem we had here was you have a load instruction, you had a sub instruction immediately following that. Now, if in between load and sub, if there was some other instruction which was brought in over here, okay, which was not dependent on this load, then obviously that could have executed in this in between clock cycle, okay, without causing any stall, and by the time the sub came in for execution, if it was fetched in the next clock cycle, with this forwarding path in place, we would have gone ahead without any stalls. So, this is another commonly used technique that we have, which is scheduling the code in order to avoid stalls. Okay. So, how do we reorder the code? Let us say for instance you had this code A equal to B plus E and C is equal to B plus F. Okay. So, this is two pieces of code that we have. So, typically how would you write it? You will have to load B, load E and then add and then store the result into A. Now, if you have already loaded B, you do not have to load it again, you just load F, add it to the value which is there, to the register which has already got B in it and then store the value in C. Okay. So, if you look at the code for that here, you have a load T1 which is let us say the first load and then load W T2, okay, and then you have an add T2, T1, T3. Okay. So, now you can see that when this add follows this load, there is a dependence here. So, there will be a 1 clock cycle latency here, okay, and then you have a store instruction, no problem with respect to that. Okay. Then again we have a load for the F, okay, and then there is an add which is B plus F. Okay. So, again this add follows the load, so there will be a stall cycle here, okay, and then you have a store. Okay. So, let us say this whole thing would have taken up about 13 clock cycles to execute in our pipeline. So, 1, 2, 3, 4, 5, 6, 7 plus 2 stall cycles, okay, so 9 plus the time taken to fill the pipeline and end the pipeline will totally take you 13 clock cycles. Now, the same thing, okay, let us see how you can reduce the stalls over here. Now, what did we say we should do for rescheduling the code? Now, between this load and this add, I have to put some other instruction which is not dependent on this load. Okay. So, we can see that from the instructions below here, I can't move the store because this is dependent on the add, but this load instruction here is independent of these instructions. So, this load instruction now can be moved into this position, which is what we have here. This load instruction is moved over here. So, now what happens? Between this load and the add, we have got one extra instruction that has come in. So, there is some distance that we have created. So, this add now will not stall because of this load. Okay. Similarly, between this load and add, okay, here also we had a stall. Now, because we moved this load up here, between this load and add now there is a 2 cycle difference, therefore, this add also will not cause a stall. Okay. So, without stalls this whole thing now will complete faster. So, it will take only 11 cycles to complete. So, the 2 stall cycles that we had here can easily be avoided if you do some simple rescheduling of the code. Code scheduling is just something which is normally done by compilers in order to avoid the stalls. Okay. So, this is another technique that we normally keep in mind. So, we have looked at structural hazards and now we have looked at data hazards. A little bit into control hazards before we can look at the actual pipeline design. So, control hazards. If you look at control hazards, as I said, control hazards are caused because of branches. Okay. So, the branch is something which determines the flow of control. Now, whenever I have a branch instruction, remember fetching the next instruction depends on the branch outcome. Okay. And the pipeline can't always fetch the correct instruction, okay, because it will still be working on the ID stage of the branch. Remember, when the branch instruction has gone to the ID stage, the new instruction has to come into the IF stage. So, IF stage does not know which address to fetch the next instruction from. Okay. We need to worry about how to handle. So, you can see if I do not do anything, whenever I have a control instruction, I will have to stall until I know the outcome of the branch before I can fetch the next instruction, whether I have to fetch in sequence or I have to fetch from a new branch address. Okay. So, this is something we have. Now, in the MIPS pipeline, okay, if you have a conditional branch for instance, then you will have to compare two registers and compute the target early in the pipeline. Okay. So, now the way the pipeline is right now, the comparing of registers and computing the target gets done only in the EXE stage, because we are comparing of registers is a operation which takes place with the help of the ALU, and that operation gets done only in the EXE stage. Okay. So, which means until my EXE stage completes the execution of the jump or the branch instruction, I cannot fetch a new instruction. So, there will be a 2 clock cycle delay before I can decide on fetching it. So, one way of reducing the number of stall cycles in this case is by adding hardware to do this calculation in the ID stage itself. So, I am reducing 1 stall cycle. In the ID stage itself, let me add some additional hardware which in case of these kind of special instructions, branch instructions, will do this address comparison and calculate the address and give it to me, so that in the next clock cycle at least the new instruction can be fetched from the correct address. Okay. So, this is something we do. Okay. Otherwise, you will have to stall on a branch. Okay. So, you can see what is happening here. So, I have a add instruction, okay, some $4, $5, $6, and then I have a branch equal which is comparing $2 and 40, and then will branch to the correct address, okay, 40. Now I have another OR instruction which is following that, okay. So does this OR instruction, can this OR instruction start in the next clock cycle? The answer there here obviously is no, because only when with this additional hardware that I have added in the ID stage, only when the address is calculated in the ID stage, in the next cycle I can fetch from the correct address. Therefore, one cycle stall will have to be introduced here, which is called as a bubble, right. So one bubble here, and then the next instruction can be fetched. Now by the time we come to fetching this instruction, we know the outcome of the branch. So either from the branch target address or from the sequential path we can fetch the correct instruction, okay. So this is what we do to handle the stalls on branches. The question that comes up is, do I always have to stall on a branch, or can I do something better, okay. The answer to that is that we use a technique called branch prediction. When we talk of branch prediction, what we normally do is we try to predict the outcome of the branch. That is, we do not know whether the branch will either go to the taken path or go through the sequential path, but we try to predict what the outcome of the branch would be, okay. This prediction could be either based on some static information or it can be based on some dynamic flow of the program, okay. There are very sophisticated techniques available for branch prediction. So based on which way the branch is likely to go, so you kind of predict which way the branch is likely to go, and based on the branch prediction, okay, you will be able to fetch from the target address earlier in the cycle and therefore avoid the stall cycles, okay. There are some very sophisticated branch prediction techniques that are used. In the MIPS pipeline, you can predict branches not taken and fetch the instruction after the branch with no delay, okay. This is something which is easy to do in the MIPS pipeline, okay. But of course, you have to remember that if your prediction goes wrong, then you will have a problem, okay. So mispredictions will also have to be handled. Those are some complications that we have, but otherwise with stalls and with additional circuitry and with some amount of branch prediction, control hazards can also be handled. So to summarize, so we have looked at the different hazards that can occur in pipelines and how they can be handled. So the different types of hazards we have are structural hazards, data hazards and control hazards. And the way we handle these hazards without any techniques is basically by means of stalls. That is, you stall the pipeline and introduced bubbles, that is, there are some idle stages that are introduced into the pipeline. Another way of handling these hazards is by using additional resources in the case of structural hazards. We saw how the additional memory is split into two, the instruction memory and the data memory in the case of the MIPS pipeline, and then use of forwarding and code scheduling to handle data hazards. We saw two examples of how forwarding can be done. Of course, this requires some additional data path to be introduced. We saw how that needs to be done, and then how control hazards can be handled by means of additional hardware. Of course, there is also something called branch prediction that is used when you are handling control hazards. Some questions to review the contents of today. Question number 1, what is a hazard? Question number 2, what are the three types of hazards that occur in an instruction pipeline? Question number 3, how does forwarding help to avoid hazards? Question number 4, what is a control hazard? Question number 5, how can it be handled? Thank you.